guys. So let's go ahead and kind of review over our periodic trends, because I know it's been a while since I've made one of these videos for y'all, and you have a test and your midterm coming up this week. So we want to make sure we are fully prepared. So the first trend I want to talk about is the atomic radius. And as we're talking about this, we're going to go through the definition, the trend on the periodic table, and why it does what it does. Like, why is that the trend that we see? And so the first thing is the atomic radius is used to measure the size of an atom, and it does that. Okay, think about radius. If you have a circle, okay, from the center to the outside of that is the radius. And so with an atom, it's kind of difficult to measure, where does an atom end and the next atom start. And so they kind of use it by half the distance between two nuclei, but essentially it's going to be the distance from the nucleus to the outer edge. I'm going to put that in, quotes, because there's not really a defined line. The outer edge is just kind of the farthest spot that an electron attached to that nucleus can be, the outer edge of an atom. And so just kind of think about it in that language. And so the trend that we see is when you're looking across, okay, and across always means from left to right, and this is across a period, which is the same thing as a row, so side to side, okay, we see that it decreases. And so when we look at these arrows, we say, okay, but I see it pointing the other way, and so your arrow always points towards the big side. So things are big over here and smaller over on the far right. And so the arrow points towards the largest side. And I like to think about it because if you, kind of color in this little arrowhead over here, it's literally the bigger side of the arrow. And so I know that it always points to the largest side. And so the question is, okay, well, why does it get smaller? Okay, because we know as we go across the periodic table, okay, we see it goes from, something with the atomic number 3 to 4 to 5 to 6 to 7 to 8. So we see there's more protons, there's more electrons, more neutrons. Like, how is the atom actually getting smaller? That is opposite of what we might think. And so the way to really think about it is to think about the attractive force, okay, between protons and electrons. So the attractive force between protons and electrons increases. Okay, so this attractive force is similar to the pull of gravity, and how even though we're adding more electrons and more protons, the protons are so much bigger that it's having a larger pull on those electrons. Its gravity is increasing as well. And so when that attractive force is going up, those protons are pulling those electrons in closer to itself because it has an increased force. Okay, so that's kind of why that happens. And so when we look at the trend as we go down a column, so this is down from top to bottom, that's kind of what that language means, top to bottom, down a column, which is also a family, also called a group. You can see all that kind of language. As you go down the periodic table, it increases, okay? So as you go down from top to bottom, it increases. So we have big down here, small up here, and so what we can see is that this bottom left corner is going to have the very biggest of both, and the top right is going to be the smallest of everything. And we can actually use these two arrows and combine them into one arrow that moves across the periodic table in a diagonal line, and it would point in this way. So if you're comparing two elements that are maybe not on the same row and not even in the same column. They don't share either of those. You can use this diagonal line to help you. And so when we think about, okay, why does the trend for the top to bottom, why does it do it? Why does it do that? And it is because the added energy levels of electrons shield the outside or valence electrons from the force. And that force, I'm not talking about Star Wars, I'm talking about that force between the protons and electrons. So if we look at some things here, so if we just kind of come over here to some blank space, let's say we're looking at lithium. Lithium is going to have 3 protons, and it's going to have 4 neutrons, and lithium is on row number 2, and so that means it's going to have 2 energy levels. Okay, so we kind of draw them as 2 rings, and it's going to have an electron and an electron, and a third electron on the outside ring. Now, the deceiving part of this model is that my protons are not nearly the same size as my electrons. It takes about 2,000 electrons to be the same size as a proton. And so what happens is as you go down the periodic table, okay, so if we go from lithium to sodium, okay, sodium's going to have 11 protons, and I think 12 neutrons. I could be wrong about that. Check your periodic table. And it's going to be on row 3. And so it's going to kind of look like this. It's literally getting bigger because of that added energy level. So that impacts the size. But another thing is that with its electrons, okay, so the second energy level can hold up to 8 electrons. So there we go, that's 8. If I have an electron on this outside, it literally has all of these on the inside that I guess you could say are interfering with the proton's force on this outside valence electron. Okay, and so it only increases from there because as you go underneath sodium, you're going to have something on row 4, and so now it's going to have 1, 2, 3, 4. And so those added energy levels physically make it bigger, but also the protons lose some of their effectiveness at attracting those outside electrons because the farther away they are, the harder it is to hold on to them. And so that really leads us into our next trend. So the next trend we're going to talk about is the ionization energy. And you might be seeing one of your vocabulary words embedded in there, the word ion. And so ionization energy is the energy required to remove an electron, which if you remove an electron, you become an ion, specifically a cation. And so this talks about, okay, how much energy does that require? So energy required, I wrote requirement, required to remove an electron. And so one thing you can think of is that cations want or commonly lose electrons, and that's because they have a low ionization energy. Cations are always going to have low ionization energy because they want to get rid of some of their valence electrons, so it's not going to require much energy. But anions are going to have a high ionization energy because they don't want any of their electrons to be removed. They actually want to find some extra electrons, and so therefore they're not going to get rid of what they do have. And so when we look at the trend, it increases across, okay? And so you can think about it if electrons are being held tighter, so that increased attractive force between the protons. So between the protons and the electrons, That's going to happen here too. And if you think about it, as those electrons are moving closer and closer, because of that attractive force, the if you have more force attaching something, then it's going to require more energy. For example, if I have a piece of yarn connecting two things, and I compare that to something that has a piece of steel connecting two things, it's going to require a different amount of energy to separate those two things because of the increased force that is connecting them. And so that's kind of what ionization energy is doing there. And it's all about location. And so that comes into play a lot with the trend. For a column, it decreases as you go down. And so it gets smaller and smaller. And so that's because of those energy levels. So the energy levels of electrons shield the valence electrons from that force. And what that does, if we look back at my wonderfully artistic picture, is if there is a force between these protons and these inside electrons, right? They're real close. That force, those electrons are not shielded at all. They're going to be feeling that force a lot. And then even with these outside electrons here, in the second energy level, okay, they're so close. But now this electron way out here, well, that force, distance-wise, it's also being spread out among those inner electrons. It's not going to be as strong. And so something can come and take one of those electrons. And I always think about it as if I was at the mall, right? And let's say this is me, okay? And I got my little hair and my bangs. Okay, this is me. And this is the little baby that I don't have. Okay. Now, if this baby is right beside me, then a kidnapper, okay, we're gonna draw the kidnapper in purple. This is a kidnapper. Okay. If there's a kidnapper at the mall where we're at, he or she, because kidnappers could be both, are gonna have to exert a lot of energy in order to get that baby away from me because it's very close. However, if I, in this second scenario, am over here, okay, this is again green little me, but my little baby that I don't have is way over here, well, then this kidnapper can get to the baby pretty quickly and pretty easily because of that distance. The kidnapper wouldn't have to exert as much energy. Okay, so distance, the literal physical distance, changes the amount of energy required to remove that electron from the presence of the atom, or in the case of my analogy with the baby and me, distance changes how much energy is required to remove that baby from my presence. And so that is how it impacts ionization energy. So if we look at our third trend on the periodic table, electronegativity, there's several definitions, but one way you can think about it is the ability to gain or attract electrons, and it's kind of the opposite of ionization energy in terms of the goal. So in ionization energy, it's talking about removing an electron, and electronegativity is the ability to gain or attract an electron, and they go hand in hand with each other. And the reason why this is if I require a lot of energy to remove an electron, then I am also probably good at gaining or attracting other electrons. And so they go hand in hand, and they share the same trends. These are the same trends, the same pattern. And that is because their reasons are also the same. So it increases across, because if I have an increased attractive force, then I can, and of course by I mean the atom, can not only keep my electrons attracted, but I can attract the electrons that actually started out in another atom. And so that increase helps with that. So between our protons and electrons. And then as I go down the periodic table, it decreases because, again, those energy levels of electrons shield the valence electrons. And so not only am I having a hard time holding on to the electrons I do have, but it's going to be more difficult to gain an extra electron. And so that's kind of the way I think about it and explain these. And so on these practice problems here, which, guys, these are the basics of the practice problems. You have to be able to do more than just this, but this is practice of just getting the basics down for our exam. If you can't do this part, then the exam will be a struggle. So if we look, there are a couple things. So if we look at question 1, it says determine which will have the smallest atomic radius, okay, in the given group. Okay, so here's the thing. When you're on your test, I'm not going to tell you the trends. You're going to have to know what they are. And so the important thing is if we look back at our notes, we see, okay, ionization energy and electronegativity are the same. Atomic radius is the opposite of it. And so what we do, my strategy for you is memorize atomic radius. Memorize that one, flip it for the others. So I'm like, okay, sitting on my test, atomic radius, I'm going to draw my arrows. Arrows point that way and down, and the diagonal one looks like that. Cool. Got my arrows down, ready to rock out this problem. Said I have K or Ca, and so I find those on the periodic table, and what you'll find is K and Ca are side by side, and so I look at my side-to-side arrow, and I see that if I were to take K and Ca on my periodic table and draw my arrow over it, it would point towards the K, which means, because it's there, that K is big and Ca is smaller. Okay, not necessarily that one is huge and one is tiny, but in comparison to each other, K is bigger and Ca is smaller. So potassium is larger, calcium is smaller. And so when I'm looking at this, I would say, okay, well, calcium is going to be smaller. If we look at fluorine versus sodium, well, fluorine is kind of up here in the corner of the periodic table, and sodium is above K, but not in the same row. And so we would use kind of that diagonal arrow, and it's pointing towards sodium. And so we would say, okay, well, that must mean fluorine is a smaller atom. And if we look at magnesium or calcium, they're in the same column, and so you would use the up and down arrow. And so you would just kind of go through it that way in order to practice. And when you get to the ionization energy questions, like in number 4, okay, you would use the arrows, same method, but instead you would say, okay, well, I flip my arrows now. Now my arrows point that way, they point up, and they point up and to the right, and we would use those. But you're always overlaying your arrows on top of the periodic table to find out, okay, comparing them to the other ones in this group, what would be the right answers. And you had homework, which was to do 2, 3, 5, and 6. That was all homework. So hopefully you did it and you understand. If you don't, come to tutoring, ask questions, be engaged. Sayonara.